In this problem, we're going to apply Ampere's law with Maxwell's correction. So what's happening here is that as this current keeps on going, this side over here is going to accumulate charge, and this side is going to accumulate negative charge. And there's this gap that is really small here, and this gap is really small so that we can apply the symmetrical arguments when we use Maxwell's equations. So what's going on is that, as you can imagine, there's going to be an electric field here that's pointing in this direction. So because there's a positive charge and negative charge here. So first of all, let us just write out what Ampere's law is with Maxwell's correction. So we get something like this. And then in our case, since we're considering the situation inside this gap here, you'll see that there is no enclosed current, so this term is equal to 0. So we only have to concern ourselves with this. So first of all, let us find the change in electric field with respect to time. So first of all, what is the electric field? And because this gap is very small, essentially we can model the electric field inside this region as two infinite plates. So recall that for an infinite plate, the electric field is equal to sigma over 2 epsilon. And so in our case, since we have two plates, we get sigma over epsilon, so it's just multiplying this by 2. And we can also express sigma, the surface charge density, as the amount of charge divided by the area, so pi a squared epsilon. So this is the electric field. And so when we take the derivative, we get something like this. So the change in charge, that's just equal to the current, right? That's what the definition of the current is. It's the change in charge. So this is the expression that you get for the change in electric field. And then recall that this is actually, what we found here is the magnitude. So this is actually a vector. So you see there's a dot product here. And in our case, since the charge is accumulating here, the change in electric field is going to point in this direction. This is going to keep increasing, and the electric field is going to keep increasing in this direction. And so so now we have to draw a loop here and to evaluate our surface integral. So let's evaluate this component here first. So evaluating this. So dot dA. So we're going to choose a loop to be something like this. So it's going to go around the arrows like this. So you can imagine if you're standing here and looking in this direction, it's going to go in clockwise direction. And if we're choosing this, then our dA is also going to be pointing in this direction thanks to our right-hand rule. So you see that our dA and our electric field is pointing in the same direction. So because of that, so since it's pointing in the same direction, we can just take away that dot product. It's just equal to 1. So all we have, so you can see that here is just constants, so I can just pull these out. We have dA. So the integral of dA is just adding the tiny pieces of the surface bounded by this region here. And so all we get is just pi s squared. So s, so I'm going to define a variable here. So for this loop over here, this radius, I'm going to let it be equal to s. So all we're getting here is just pi s squared. And this is going to be equal to the line integral. And then as the electric field is increasing in this direction, it is going to generate a magnetic field that is going to point in this direction. So in the direction of this loop here, thanks to the right-hand rule. And thanks to that, we know that this is going to be equal to the magnetic field times the length of the loop, so 2 pi s. So all we have to do now is just divide this over to the other side. And you'll see that the pi's they cancel out, epsilon it cancels out, one of the s they cancel out, and you get mu I s divided by 2 pi a squared. So this is your answer. And then so this is the magnitude of the magnetic field. So the direction is going to be the clockwise direction. So from the point of view of standing here and looking in this direction. So it's clockwise.